Welcome to Dr. BT's Chemistry Essentials, A-level chemistry made easy. So alongside the other video where we've looked at ionisation energy and the trends in the first ionisation energies, this video is going to focus on successive ionisation energies and what that tells us about the electronic structure of an element. Now, in the previous video on first ionisation energies, we defined what ionisation energy is. So I'm very quickly just going to go through what ionisation energy is and what we mean by successive ionisation energies before we talk about how this tells us any information. So ionisation energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms or ions. The equation that shows the first ionisation energy of sodium is shown below. And we dealt with the trends in first ionisation energy in our other video on first ionisation energies. But what we're interested in now is in successive ionisation energies, so those that aren't just first. So the second ionisation energy of sodium will involve taking the product of the first ionisation energy and ionising that one more time. And so we start with something that is a positive cation and become 2 positive cation. Something to note is the product ion that you form, the number of the charge there tells you exactly what ionisation energy it is. So here we have a 2+, so we know it's a second ionisation energy. Obviously, previously, this was just 1+, and that was our first ionisation energy. I want you to pause the video now, and let's go ahead and do the 5th ionisation energy of sodium. I want you to come up with the equation that shows that. Okay, so if you have written down this as the 5th ionisation energy, so obviously we know we're the 5th, so we've got sodium 5+ as the product. And because it's always iterative, there's only 1 electron that's ever lost in this oxidation reaction. And so for it to have only lost 1 electron, it must have originated from sodium 4+. And just being hyper aware of the state symbols, they're both gas because it says here that we've got to remove it from 1 mole of gaseous atoms or ions. So anything beyond first ionisation energy is what we call successive ionisation energies. So now we're going to look at some data to do with the successive ionisation energies, and in this case we're looking at aluminium. So you can see from this data table that our ionisation number is increasing, and with that the ionisation energy is also increasing. So that's the first thing that we can note down. Now we can explain this as the electrons are constantly being removed from an increasingly positive ion. And this leads to less repulsion amongst the remaining electrons. And this in turn therefore means more energy is required to remove the next electron. So let's just illustrate that with just looking at the first and second ionisation energies of aluminium here. So the equation for the first ionisation energy would look like below. And this 578 kilojoules per mole was required to remove this electron from its attraction to the nucleus in the original aluminium atom. But then in our second ionisation energy, we need to remove the second electron from the pull to an Al+ ion. And so in this aluminium cation, there is less repulsion in the remaining electrons, and so if there's less repulsion, there's more of a nuclear attraction between this electron and the nucleus, and so we require more energy to actually remove this. And that's why we can see this rise here to 1817. And this trend carries on increasing as we go through the ionisation because we've got that increasingly positive ion. However, some of you will notice there's some changes in the data, some big jumps. And these big jumps give us some evidence for the structure of the shells and the subshells that we have in our element. Pause the video now and see if you can see the different big jumps in the ionisation energy. So you might have identified the big change is here between the third and the fourth ionisation energies. You can see between the first and second and third, it's roughly about 1,000 each time. But then we seem to have this massive increase between the third and the fourth of a 9,000. And then beyond there, there's still a high increase, but not nearly as much, of roughly about 4,000 to 5,000. And so this massive increase of 9,000 tells us something about the structure of our atom. Now, we've been told it's aluminium, and hopefully you can understand from the periodic table that aluminium is in group 3. And so this data allows us to work something out about the electronic structure. And that's that the number of electrons removed before the large increase in ionisation energy, so here we had 1, 2 and 3 before the large increase, gives you the group number of which that element belongs to. And so here with aluminium, which we know is in group 3, we know that the number of electrons removed should be 3 and before the biggest increase, and we can see that here. Now, to look at this data in just a bit more detail, we're just going to look at the electronic configuration for aluminium. So aluminium on the periodic table has a proton number of 13, so we know it has 13 electrons. And if we are just to put the electronic configuration of that, then what we're going to do is we're going to have 1s2, 2s2, 2p6, 3s2, and then 3p1. So you can see here, it asks some of these ionizations involve the removal of an electron from an S subshell, and you might be asked to link this data here to the electronic configuration. So if they were to ask you which ionization numbers were linked to the removal from an S subshell, we know that the first ionization energy is for P1. That leaves the next two ionization energies where we've got 3s2 going to 3s1 and the 3s1 going to 2p6. The second and the third are from an S subshell. And then that allows us, first of all, to know what group it's in because it's jumped up there. And we know that the shell there has been moved down to the 2 shell. The next 6 are in our P subshell. And so that leaves us to then be able to work out that the 10th and the 11th are the electrons from the 2s2 subshells. We would then expect on the 12th and the 13th ionization numbers for there to be a big increase from this 42,655 as we move to the next shell, the 1 shell. So now it's time for you to show that you understand this. What I'd like you to do is sketch out a different type of data form here, so a graph of the number of electrons removed on the x-axis, and on our y-axis we've got ionization energy. I want you to sketch the type of graph that we would see if we had sodium as our element that we were looking at the successive ionization energies of. So pause the video now and have a go. Okay, so hopefully you've constructed a graph. What we first needed to do, and hopefully you approached it, was look at the fact that the sodium atomic number is 11. It's in group 1 and in the S block, so we know that it is going to have its outermost electron in an S subshell, and also it's in period 3. So we know that that last electron is 3s1. And we can use that to construct the overall electronic configuration. Now, because it is in group, so we remove the first electron, 3s1, and we plot that. As sodium is a group 1, we're going to see a massive increase after this first electron. So we're going to see a big increase when we remove the 2p6 electron. And then for the next electrons, then we're going to have a steady increase. And now as we enter the 1s2, there's going to be another increase. And so to bring this sketch all together, you can see that we have massive increase, goes up to, and then another sharp increase as we move between the 2 shell to the 1 shell. And then finally, we've got our n equals 1 shell here, which equates to the 1s2. Okay, so finally, just to check that you fully understood this, I'm going to display a graph in a moment, and what I want you to do is tell me exactly what group this element is in, and then come up with its electronic configuration. So here's the data that you're being given. Here's the graph. So we want to know what group this element is in, and then with the clue of it being in period 2, exactly what the electronic configuration for this element is. Okay, so revealing the answer now. Hopefully you have worked this out to be in group 6. The reason being we've got 1, 2, 3, 4, 5, 6 electrons before the big jump. So we know it's in group 6. And given that it was in period 2 and we have 8 electrons overall, we know that the element must be oxygen that has a proton number of 8. And therefore, its electronic configuration is 1s2, 2s2, 2p4. So if we were to assign this to the different electrons that are being removed, this is our 2p4 electron that is being removed. This is our 2p3, 2p2, 2p1. This is then our 2s2 electron that's being removed. This is a 2s1 electron that's being removed. And finally, we've got our 1s2 and our 1s1 electrons being removed. And so, therefore, we've got all of the electrons and all the successive ionization energies of oxygen on this graph. So this video and the other video on first ionization energies concludes all that you need to know at A-level chemistry about ionization energy, trends and patterns. I hope you found this video useful. If you have, ensure that you like it and ensure that you subscribe to the channel Dr. BT's Chemistry Essentials for more videos covering A-level topics in a clear and concise way.